Hello, everyone, and welcome to this explainer module. I am Dr. Ramani Bai, Associate Professor, presenting alongside Mr. Taha Muhammad Jassim from UCSI University, Kuala Lumpur. A huge welcome to all our engineering technology students, civil and mechanical engineering students, and of course, our industry engineers tuning in. Today, we're your instructors, and we're going to build that absolutely critical bridge between the statics formulas you stare at in the classroom and the very real-world infrastructure and industrial maintenance operations you're going to face in your careers. So here is our game plan for today's session. We're going to cover soil grain size analysis, soil moisture and density, and cement setting time. Along the way, we've got a few lab assessment quizzes to keep you on your toes, and we'll wrap it all up with a core concept summary. Let's dive right in. All right, kicking things off with Module 1, Soil Grain Size Analysis. This is quite literally the foundation of structures like earth dams. Let's break down the operational steps. You'll assemble your sieves in descending order, largest openings at the top, finishing up with the pan at the bottom. Pour your dry sample in and fire up the mechanical shaker. As you watch this 3D animation of the shaker vibrating the stack, keep in mind that for accurate particle separation, you have got to run the shaker for exactly 10 minutes. Not 9, not 11, 10. Afterward, you'll carefully weigh the soil retained on each individual sieve. Okay, let's look at the math. To find the percentage retained on each sieve, you simply take the mass retained, divide it by the original sample mass, and multiply by 100. So, for example, if you started with 500 grams and your sieve retained 9.7 grams, your calculation is 9.7 divided by 500 times 100, which gives you 1.9%. Now, here is a crucial point for your lab assessments. If you calculate your total recovered mass and find a loss of more than 2% of the initial soil mass, your test is officially unsatisfactory. You'll have to do it again. Precision is literally everything here. Once you calculate the cumulative percentage passing for each sieve, you're going to plot a semi-logarithmic graph. Grain size goes on the logarithmic x-axis and percent passing on the y-axis. From this curve, you need to extract D10, D30, and D60. And listen, these aren't just arbitrary numbers to write down. They represent the exact particle diameter where 10%, 30%, and 60% of the soil sample is finer. They are the vital metrics that dictate the fundamental grading profile of your entire soil sample. So, what do we actually do with those numbers? We plug D10 and D60 right into this formula. Cu equals D60 divided by D10. This simple calculation gives you the coefficient of uniformity. As engineers, we use this alongside the coefficient of curvature to officially classify the soil as either well-graded or poorly graded. Time for a quick pop quiz. I want you to really think critically about the statics principles we just applied. Why are we spending so much time in the lab shaking dirt through sieves? What major, real-world engineering application relies directly on these precise grain size distribution results? If you said infrastructure survival, you hit the nail on the head. As you can see from these real-world examples, well-graded soils exhibit significantly better compaction and shear strength. This makes them the absolute ideal choice for load-bearing road bases, determining the stability of heavy industrial machinery foundations, and designing those critical filters for earth dams. So to sum up Module 1, grain size directly dictates structural stability, period. Moving right along to Module 2, Soil Moisture and Density. This is all about bearing the structural load. For this procedure, we rely on the standard oven drying method. First, you record the mass of your wet soil in a can. Then, as simulated by this thermal animation, you place it in the drying oven overnight. Pay close attention to that temperature setting, exactly 105 degrees Celsius. If you fail to maintain this exact temperature, you might leave residual moisture behind, or even worse, burn off organic matter, which will completely ruin your density calculations. Finally, you record the dry mass and calculate the difference. Let's take a look at some actual lab data from 2 samples. To calculate this, you take the mass of the pore water and divide it by the mass of the dry soil. Notice how sample B has a moisture content of 10.53%, which means it's retaining slightly more water than sample A's 9.68%. In a real-world scenario out in the field, this slightly higher water retention is a huge clue. It indicates a higher presence of fine particles, like clay or silt, in sample B.
And here is the core engineering concept you really must grasp. It's an inverse relationship. As moisture increases beyond optimal levels, that excess water occupies pore spaces but adds absolutely zero solid structure. Consequently, the lower dry density reduces the proportion of solid load-bearing particles per unit volume. Basically, your soil's structural density fundamentally decreases when water takes up the space that solid rock and sand should be occupying.
Pop quiz number 2. We've just calculated moisture and density in the lab, but how does this calculation translate to the heavy machinery, the concrete, and the daily life on a massive job site? Why is determining this exact in situ unit weight so critical? Well, if you get that bulk density wrong in the lab, your calculations for true bearing capacity will be dangerously off, and that leads to foundational settlement. Imagine a factory floor settling unevenly. It would completely misalign modern industrial maintenance lines and cause catastrophic structural failure. So, to wrap up Module 2, moisture and density tell us exactly what the Earth can hold safely. All right, shifting gears to our final material, cement. Module 3, cement, setting time. It really is a race against the clock. To run the Vicat apparatus test accurately, which you can see visualized here in this 3D penetration animation, you first need to mix a paste of standard consistency. This typically requires adding 25 to 35% water by weight of the cement. You fill your Vicat mold, smooth the top out, gently lower the testing needle until it touches the surface, release it, and then record the depth it sinks. You just keep repeating this process until the cement hardens enough to resist the needle entirely. Now here is a magic number you definitely need to memorize for your practical assessments: 30 minutes. In our laboratory observation, 30 minutes was the final setting time. This precisely marked the exact moment the needle's annular attachment no longer left any physical impression on the surface of the cement paste. Final pop quiz for this explainer. Imagine you're the lead engineer on site. The chemistry of your cement mix is simply not matching the construction schedule. What are the severe, real-world consequences if that cement sets outside of its expected, lab-tested timeframe? Basically, it's a disaster either way. If it sets too fast, you just don't have the time to pour and vibrate it properly. You end up with weak, unworkable concrete filled with dangerous structural defects. On the flip side, if it sets too slow, it severely reduces early structural strength, and the entire project timeline grinds to a halt, costing millions of dollars in delays. This proves exactly why your accurate lab testing is absolutely non-negotiable.
Let's wrap this all up with a quick core concept summary to give you the high-yield takeaways for your upcoming assessments.
Lock these strict procedural thresholds into your memory. You are permitted a maximum 2% loss of initial soil mass during seeding. You absolutely must maintain exactly a 105 degrees Celsius oven temperature for moisture drying. You're looking for that 30-minute final setting time for standard cement. And you need a 25% to 35% water ratio to achieve normal cement consistency. Remember, precision in the laboratory is what guarantees safety out in the field. And honestly, mastering these foundational tests doesn't just mean you pass a class. As this quote regarding soil moisture highlights, accurately gathering this data scales up to solving massive global engineering and daily life challenges. The skills you're learning right now directly translate to managing agricultural droughts, stabilizing ecosystems, and designing resilient infrastructure that can withstand extreme weather events. Because at the end of the day, every skyscraper, every earth dam, every highway, and every industrial maintenance facility relies completely on the exactness of the data you gather right here in the lab. Thank you so much for joining Mr. Taha Mohamed Jassam and me for this explainer module. As you prepare for your assessments, I want to leave you with this final thought. When thousands of tons of static load are resting on your foundation, are your lab measurements truly precise enough to bear the weight? Keep exploring, keep questioning, and we will see you in the lab.